Welcome back to week 4 of our course, Boltzmann Law, Physics to Computing. This is the fifth and last lecture for this week. Now, in the earlier lectures, we established this basic framework for describing quantum spins, how you write down the energy matrix or the Hamiltonian matrix, and how you obtain the probability matrix or the density matrix, and then deduce the expectation values of different observables. Now, one use for a system of quantum spins, this what you might call generally adiabatic quantum computing using qubits, would be chemical structure calculations, which can be cast in the form of a H matrix describing the interactions of many spins. But as I pointed out, the challenge there is how to implement the complex interactions in the actual hardware. Now, in this lecture, what we'll talk about is a possible application in which there has been a lot of work, and this requires relatively simple interactions. So this is what's generally referred to as quantum annealing. Okay. Now, let me start from a problem that we discussed in lecture 2, actually, where we talked about this problem of optimization using classical spins. And there the idea was how to design the interactions so that the lowest energy state indicates the solution to some problem we are interested in. And this was done with classical spins. That was lecture 2. And we used this min cut or max cut problem as an illustration. So the idea was, if you have, say, a bunch of nodes, I show, say, 6 nodes, of which some are connected strongly and some are not connected, and there's a connection matrix describing these connections. And the problem is to find a way of separating them into 2 separate groups of 3 nodes each, such that the connections that you are cutting when you break them apart is a minimum or is a maximum. So you could have a min cut problem or a max cut problem. And what we showed there is that there is a simple algorithm for choosing these bias terms x and the interaction terms w. Given the connection matrix, you can choose them in such a way that the lowest energy solutions will actually solve the problem you're interested in. And in that context, as I'd mentioned, that the problem we want to solve is constrained optimization, which means when you break it up into groups, they should have equal number. That's a constraint you want to impose, and that's imposed through these red terms. So these were all discussed in this lecture in week 2. Now, and what we showed was that if you consider the min cut problem, for example, you'd find that the highest probability or lowest energy peaks are the following configurations, which are kind of equivalent. It's just that the zeros here are replaced with ones there. So when you look at that 0, 0, 1, 1, 0, 1, what it tells you is one group should be 1, 2, and 5. Those are the zeros. And another group should be 3, 4, and 6, which are the ones. And if you look at the other solution, you come to the same conclusion. And in this case, just looking at the graph, you could have guessed it, because you see 1, 2, and 5 are connected, 3, 4, and 6 are also connected. So the best way to separate it into 2 groups while cutting a minimum number of bonds is by making the 2 groups 1, 2, 5 and 3, 4, 6. But as I mentioned, many problems, especially with more nodes, the answers may not be obvious. And in this case, the min cut is obvious, the max cut isn't. So, but the point is that if you set up these nodes with these x and w matrices properly, then it will solve the problem for you. Now, going forwards, what we'll be trying to do is translating this into a system of qubits and describing to you what the quantum system can add to this story. That's what we'll be doing. But before we go on, let me just replot this graph, not as a 2-dimensional thing, but more in 1 dimension. What I mean is, here the way we did it is we had 6 bits, and so we put 3 on this axis and 3 on this axis. So you had 8 here and 8 here. But what you could do is plot it like a linear graph with 64 items on a single axis, which is 2 to the power 6. So all 6 combinations right here. And in that case, this first solution would look like a 13. Why is that? Well, it's like you take this binary number and convert it to decimal. So you have a 1 in the first place, which has a weight of 1. Next one is 2, but the next one is 4, and then the next one is 8. So you've got 1s on 8, 4, and 1, which makes it 13. The other one has 1s on this 2, 16, and 32, which makes it 50. So those are the 2 peaks you'd expect to see if you plotted it kind of simply in a like a one-dimensional plot instead of this 2-dimensional thing. Okay? So going forwards, you'd be using this plot. Okay. Now, in solving problems of this type, there is a common difficulty that I didn't talk about earlier, which is that when you have many nodes, I mean, this is not a problem you'd encounter with 6 nodes usually, but it's with many nodes, what could often happen is that as you try to find the lowest energy states, when you're sampling, I mean, you could get stuck in other states which are not really the lowest energy. Of course, if you're doing the actual Boltzmann calculation, you'd always find the correct peaks. But as I've mentioned before, when you scale up, the Boltzmann calculation is impractical because it's 2 to the power n, and you try to do this sampling. So you calculate these time samples one after another and plot a histogram. And in that case, samples often tend to get stuck in relatively higher energy minima instead of going to the lowest one. If you take many, many samples, wait a long time, theoretically it should always get there, but with a reasonable number of samples, it often may be difficult to lock in on the right answers. And so one solution that people use is what's called annealing. And that's the idea is that this energy, they multiply by a number E0, some constant, which doesn't change the structure of this. But what that does is let's say when E0 is 0, then all states are equally probable. And then as you increase E0, gradually the correct peaks rise up. So annealing consists of starting from E0 equal to 0 and gradually increasing it. Which, if you think about it, the probability, this E that we have been using in weeks 2 and 3, kind of came from the Boltzmann law for physical systems, which we discussed in week 1. And there, all the actual physical energies were normalized to kT, T being the temperature. So when you put E0 equal to 0, that's kind of like putting a very high temperature. And when you gradually increase E0, that's like gradually decreasing the temperature. And that's the origin of this word annealing. Because in physical systems, when people are trying to grow an ice crystal, then the crystalline state is like the lowest energy. But we all know that the solid often gets stuck with many defects in it, which are really not necessarily the lowest energy. But they're getting stuck in these intermediate states. And one way to get rid of defects is to heat it up and gradually lower the temperature. So it slowly goes to the lowest energy state. So that's kind of the origin of the word annealing. And in this case, of course, we are not changing the physical temperature or anything. We are just changing this energy function, which is multiplied by a constant. So the basic function is the same. You just change the constant multiplier. Okay. Now, what we want to talk about is what would be the quantum version of this and what would the quantum version add to the story. And here, as I had mentioned before, when translating to the quantum spins, it's more convenient to work from the bipolar formulation. Namely, you see, you usually have been using in weeks 2 and 3 the binary formulation where the spins had values 0 and 1. But the bipolar one, where it's -1 and +1, that is the one that translates naturally into the quantum formulation, into the quantum spins. Indeed, these H and J for a particular problem don't even need to be recalculated anymore. You can just use whatever's right here. Whereas if you're using binary, you couldn't just use the X and W here and translate it into the quantum version. So what you could do is then, if you have the binary answers, you could first transform to the bipolar. And in 2.4, in lecture 2.4, we had discussed how you can take your W and X and transform it into J and H. So that's the first step. Go to the bipolar version, and once you have the bipolar version, you can get the quantum matrix formulation, where instead of E, we now have the H matrix, simply by replacing M with sigma Z. So the Z component of the quantum spin. So MR MQ becomes sigma ZR sigma ZQ. And the point is that these coefficients H and J remain unchanged from what they were in week 2. You could use exactly the same, and you just have the qubit version of the original problem. Of course, if that was all, then you'd say, well, why do I even want to do it? The classical one is much simpler. We can go from there. But what the quantum one lets you also do is add a x-directed spin, add other terms to it that are not in the z direction. So you could, for example, add a term like this, which would correspond to, I guess, an energy term that involves the mx component. Now, annealing, classical annealing, the way it works, as we discussed, is that you gradually increase E0 from 0. So you start at 0, so all configurations have the same energy, and then gradually you increase E0, and that's how the peaks rise up. With quantum spins, what you could do is, you could keep E0 fixed, whatever your normal value is, but you gradually decrease the H, this transverse H, from a large value. And this is what's generally referred to as quantum annealing, this possibility. This is something you couldn't have done with your classical spins. Now, just to give you an example, so with E0 equals 1 and no H along the X direction, we have this solution I had shown before, 2 peaks at 13 and 50. Now, if you were to reduce E0, which is classically like increasing the temperature, then what happens is a lot of the other possibilities rise up, right? And as I said, if you had reduced it even more, they would have risen up even more. In the limit of E0 equals 0, everything would be equally likely. And the point I'm trying to illustrate is that if instead you kept E0 at the original value 1 and just put a big Hx, it would have much the same effect. When you put 15 here, for example, you notice how all the others have risen up. And so you could use this to do what is called quantum annealing. So from 15, you could say lower it to 7, and it would look something like this. You can see all the other peaks are now getting suppressed. Just as in classical annealing, if you gradually increased E0, that's what would happen. These would gradually get suppressed and would eventually go here. So that's how the quantum annealing is supposed to work. So it gives you a way of doing annealing while keeping the E0 fixed, but you're changing this H. And why would you think that might be better than classical annealing? Well, there is a theorem that says that when you gradually change a parameter in your Hamiltonian, if you do it slowly enough, that if initially it was in some ground state, then it will stay there and eventually you'll actually get to the ground state. There's a theorem that says you can do that. Whereas in the classical case, there is really no theorem that guarantees that you'll get to the ground state. Now, in practice, how well this will work, how slowly you have to go to actually take advantage of these are all still debated and pretty much up in the air. So there have been demonstrations of various kinds. There's a lot of work that has gone into this. But the motivation is that quantum annealing might allow you to get to the ground state more reliably than the classical one. Now, why does the X term work? Why adding this X term help? Well, one way to think about it is think of what we discussed in lecture 1. We said that if you put an H, then the expectation value of mz is given by tan hyperbolic h cosine theta with a minus sign. So if you put an h in the x direction, that corresponds to theta equals 90 degrees, in which case cosine theta being 0, it says that the expectation value of mz is 0. What that means is that plus 1 and minus 1 are equally likely. And of course, if plus 1 and minus 1 are equally likely, that then tells you that all the states become kind of equally probable in that case. So that's kind of how the Hx works. Now, why the h in the x direction makes these up and down equally likely, you can get a little more insight if you actually go from density matrices to wave functions, which is not always possible, and in the next week we'll discuss this much more. But you see, if you put a large h at 90 degrees, you can show that the density matrix takes this form, because you see theta is pi over 2, so all these cosine theta terms go away, and sine theta is 1, and the tan hyperbolic becomes 1. So you get this matrix, which you can factorize into the product of this psi and psi dagger, where psi is like the wave function, and the wave function is plus 1 and minus 1. And as we'll discuss next week, there are systems where you can take the density matrix and factorize it. And in that case, you can think in terms of a wave function, which is a little easier because it's just got two components as opposed to the density matrix, which is a matrix. And here then the first component tells you the probability of plus mz, and the second one tells you the probability of minus mz. I mean the square of the wave function. So when you look at the wave function, it immediately tells you that both are equally likely. So this is what we'll take up next week, I guess, more of this, because next week most of our discussion will be in terms of wave functions. Okay? So I guess it's time to then finish up this week. What we have done is introduce the basic framework for discussing quantum spins, how to write the H matrix and the density matrix and deduce the expectation value of observables. And next week we'll go on to this, we'll make this transition from what we discussed this week, which is adiabatic computing, to what is called gated computing, and where we'll talk much more in terms of wave functions. Thank you.